All right, let's look at a rocket problem. A spy tracks a rocket through a telescope in hopes of determining its velocity. He is 10 kilometers away from the launch site, and his instrument shows that the angle between the ground and the telescope is changing at a rate of pi over 12 radians per minute when the angle is pi over 6 radians. How fast is the rocket going at that time? So first, let's draw a picture. Draw my person, his telescope, our rocket. So we've got this line going up to the top of the rocket. There's the launch site, and there's the person. So the angle that's created from the instrument, so from his telescope to the ground, we can call theta. I know that the distance between him and the launch site is 10 kilometers. And I'm just going to call this h, the height of the rocket. So let's define our variables. So theta is the angle between the telescope and the ground. And h is the height of the rocket. Oops. All right, so dh dt is what I'm solving for. I'm solving for how fast, what's the velocity, so what's the rate of change that this rocket is making. So that's what I'm solving for. I know that the rate that the angle is changing is at a rate of pi over 12 radians per minute. Okay. So we know we're trying to find out dh dt when the angle is pi over 6 radians. So again, we can't put that value into an equation right away until after we've taken the derivative, because that value, that theta, is going to be changing constantly as the rocket is going up. So what we need to do is find a formula where we can relate theta and h to each other. So when I think about this, I think about the fact that we've got a side, which is adjacent. We've got an opposite side and the angle. So the trigonometric function that goes with opposite and adjacent sides is tangent. So we can set up a formula that relates theta and h. So the tangent of theta equals h over 10. So now I can solve for h by multiplying 10 to both sides, and I get that h equals 10 times the tangent of theta. So now that I have this, now I can find the derivative. So I found a formula that relates those two variables. Now we'll take the derivative. So the derivative of h with respect to time is 10 times the derivative of the tangent of theta. So the derivative of the tangent of theta, we're going to have to use the chain rule here. So the derivative of the tangent function is the secant function. We'll do it with respect to theta. And then we still have to do that derivative of theta using that chain rule, because theta is a function of time. All right, now that we found the derivative, now I can start to substitute in these values. So when I do that, I get dh dt equals 10 times secant squared of the angle, which the angle, I'm looking for what is the instantaneous velocity right at pi over 6 radians. So when that telescope to the ground is at pi over 6 radians. And then times the rate of change of that angle, which is pi over 12. So when I go through, simplify that out, I end up getting that dh dt is equivalent to 10 pi over 9 kilometers per minute. So this means that the rocket is going at a rate of 10 pi over 9 kilometers per minute when the spy's telescope is at an angle of pi over 6 radians. Water pours into a large rectangular tank with base 2 feet by 3 feet at a constant rate of 5 feet cubed per minute. Determine the rate at which the water level rises. Okay, let's draw an image of this. So if I've got a rectangular water tank, again, don't judge my drawing. Okay, kind of looks like that. Hopefully you can visualize we've got water. The water's pouring in, so obviously that water is going to be getting more. Okay, so I've got a picture of it. So it's a rectangular tank with a base of 2 feet by 3 feet. So let's label those pieces. So I've got 2 feet, 3 feet. Okay, and we know that I'm looking for the water level. So let's call H this water level. Okay, so let's let H be the water level. So that's going to be in terms of feet. Okay, we know that the rate that the water is pouring in is at 5 feet cubed per minute. So if we're looking at, when we hear that, that should hopefully tell you volume. It's how much it's changing. Again, it's how much water is going in. That's the volume of water that's getting put in. So let's let V equal the volume of water in terms of feet cubed. So then if I was looking for, I'm solving for dH dt, and that's going to be feet per minute. And I know dV dt is 5 feet cubed per minute. Okay, so again, I'm solving for that. I know I'm trying to figure out how fast is this water's height increasing over time. Okay, so I'm solving for that dH dt at specifically when that volume is going. Okay, so if I'm trying to find that, let's see if we can find some type of relationship. So if I'm relating these quantities, we know the formula for the volume of a cube is length times width times height. So I know I've got 2 times 3 times h. So I've got a formula, V equals 6h. So we've got the hardest part down, which is finding that formula that relates the two quantities. So now we'll go through and we'll do that implicit differentiation to get this in terms of rates. So the derivative with respect to time of the volume equals the derivative of respect to time of 6h. So dV over dt equals 6 times the derivative of h with respect to time, because again, we're finding the derivative with respect to time. These are functions of time. Those are going to change as the time changes. More water is coming in. Okay, so now let's plug in what I know and what I'm solving for. So I know that the volume is increasing at 5 feet per second per minute, feet cubed per minute. I don't know that dH dt, so solving for dH dt, I get 5 over 6. And that's going to be feet per minute. So we would say the water level rises at a constant, sorry about that dog, he's really cute if you could see him, rate of 5/6 feet per minute.